Hello, everyone. First, I want to thank you that you're still here and you didn't run away. So really appreciated this. I know that we'll be late, and so I'll try to be as fast as quick as possible. Last time I had 5 slides, now I have 10. So, but we'll finish on time, I promise you. So my name is Vihar, this guy here, and this work is totally credited to the other chaps here that you can see, especially Navjeet, who did most of the work, and yes, Navjeet Bagga as well. And these are, unfortunately, they couldn't come from India because for different reasons and time zones and everything else. So I'm here, the messenger. So don't shoot the messenger. Usually people say this. So the messenger will try to explain to you what we do in general. So I work in device modeling group in Glasgow. These guys here on the back, some my postdoc and PhD student, and we simulate devices. So what I mean by this, we simulate transistors mainly, electronic devices, and also we are trying to do some biosensors, and we can talk about this later, but this is more or less on the field of biosensors / electronic devices and transistors. Okay, so let's start and let you go in 10 minutes to go and enjoy the coffee in the nice conference. So it's my first time here actually in this conference, so far I really enjoyed it, and I hope I'll see you again at some point in the future. And what I'm going to say is just I'm going to tell what is a FinFET device. How many of you know what is FinFET, because this can save us a lot of time? Okay, so I would say what's a FinFET device. There's something which is called GIDL and DIBL. How many of you know this? 2, 3. Okay, I'll try to explain this a bit quickly. And after this, I'll show how you can use hydrogen sensors in simulation to optimize your design. So more or less, if you probably heard Apple just publish their or start selling their new phone again, and it has 19 billion transistors, right? And in this room, we're probably around 30 people, so we probably have around, I don't know, roughly on average 10 billion transistors each of us. So we probably have around 40 billion transistors here in this room only. So this is the most produced device ever from humans ever. So nothing else can, not the sparrow, not the needle or anything else. This is what it is. So one flavor of these devices is this guy who is called FinFET. So the FinFET, I hope the guys online as well can hear. So the FinFET device is basically a tin, and it's looks like this. You have a source and a drain and a gate, and it has 2 flavors. It has one is called silicon on-insulator. Basically, you have it on the surface of a silicon box, and this other guys, it looks like this. It's called bulk. It was introduced in Intel in 2014 to make it better and keep the Moore's law going. Now what you have in your phone most probably is nothing which is called nanosheet or nanowires, which unfortunately for Intel, they cannot make it. There are only 2 companies on the planet that can make this, TSMC and Samsung. So in your phone, the latest technology is going to be nanowire or nanosheet, but which is exactly the same thing, but instead to say this, it stays like this. So you have 2 or 3 nanosheets where we can talk about this later. So why we want to do nanosheets and how this is linked to the sensors here. So these devices, it's a transistor, it's an electrical device. You measure charge or current. So you measure current, and this current is modulated by charge that can be trapped on the surface. There is some another type of device which is called junctionless nanowire transistor. So if probably heard most of you CMOS, complementary metal oxide semiconductor, to make an inverter or to make memory or anything else, you need NMT type transistor, and you create flash memories or inverters, and it's what you create your switch here, 0 or 1. So this guy here is junctionless, which means it has doping, which is exactly the same all the time, N or P. We're not going to go in details, but it's better than the other for something which is called short panel effects. Trust me, we don't have time for this. So the other thing what you can think about this, how am I going to make this thing sensor? So if you want to think at least from conceptual point of view, what you can do, you can put a metal on the top. I hope you can see this, which is palladium metal here. And this palladium metal can absorb hydrogen. This hydrogen literally penetrates in the crystal of the palladium, and it's absorbed as a sponge. When it does this, what is happening is create something which is called trapped charges. Trapped charges is very typical. So this concept is used a lot of in memory design and transistors, and people talk about trapped charges all the time. So from simulation point of view, for a sensor, what you have is you have a hydrogen molecule, which when penetrates in the palladium creates something which is called dipole. So the dipole has positive and negative side, and these dipoles can flip, and they can move left or right, and depends on the amount of the dipoles that you have and the distance from the channel. So if you imagine this is the nanowire, so you have the device here, So depends where is the dipole relative to the channel, and depends what is how many dipoles you have. You modulate the channel here in the middle to modulate the current. So this is what we are going to do. And in this case, the modulation of these charges that are on the surface of the nanowire are proportional to the concentration of the hydrogen. Think about this in this room. So palladium, as I said, is the way to capture the hydrogen. Now, this is GIDL and DIBO. Again, I'll try to explain this very quickly. What it means, this is that something in this device is called short channel effects, which is kind of misleading because short channel effects in transistors exist in the last 30 years, when transistors were microns. So now the transistors in channel length are about maybe 20, 30 nanometers. And this short channel effects are very well pronounced. So the bottom line is that if you have short channel effects, you cannot turn off the device. If you cannot turn off the device, you cannot switch it off, which means that you cannot have a switch. Simple as this. And these effects like GIDL and DIBO makes your RF miserable, bottom line. And the GIDL stands for the fact that when you modulate the gate voltage here, you kind of create a tunneling from the source to the drain, and the electrons are tunneling and you cannot turn off the device. And DIBO is very similar, but you don't modulate the voltage on the gate, you modulate the drain bias. So you have source and a drain, you modulate the drain bias. The channel is very short. And what is happening here is that instead of rectangular barrier that you see inside of the channel, when you make it shorter, it becomes triangular, right? So all of these guys, or all of these two effects, have impact on your device performance. So the bottom line of this slide is that if you want to simulate your sensor correctly, you need to have the right physics. And the right physics, unfortunately for us, is changing a lot when you move from something that is 20 nanometers, something that is 10 nanometers, and you need to enter all of these effects, which are called DIBO and GIDL. So this is the bottom line of this slide. Okay, so what we do, we implemented the device, or my colleagues implemented the device in the simulator called Centaurus, doesn't matter, commercial code, and they calibrated to experimental data. And as you can see here, you have a quite good match between simulation and experiment. Now, how I make it sensor, right? So I need to plug somehow the biology or the hydrogen or the chemistry inside. So if you make a device, and any device now that you have in your phone, the gate is metal on the top. So this guy here is metal, right? Can you see it's metal? So if you make metal, usually it's copper, because you cannot make a uniform coating layer of this copper metal, usually you have grains, and these grains have different work functions. And because they have different work functions, they pin the Fermi level on a different place. And because you pin the Fermi level on a different place, you have a variability depending on the size of the work. So what you do here is very similar. So you represent your concentration of hydrogen in the air. So if you think about this, the concentration of hydrogen in this room, by a metal work function of this metal on the top, which is palladium. So what I'm doing is when I increase the amount of hydrogen in the air, I'm modulating the work function, which is the surface property of the metal, which modulates the channel or the current inside of the channel via electrostatic control and dipole. And if we go in details, what you're going to see here is that basically we have a device which is 30 nanometers long, it's 10 nanometers width, and 30 nanometers long. So this is what is the device. Literally looks like this. Okay, so we want to evaluate if this thing works. And what we did, we just, or my colleagues did, they measure voltage threshold. So voltage threshold tells you how, when you turn on and off the device, where is exactly the point that this device becomes from off state to on state, which becomes from 0 bit to 1 bit. So the voltage threshold can be measured. And when you can see here what is happening when you increase the part per million in the air, the hydrogen concentration in the air, the voltage threshold increases, which is normal. I'll explain to you in a second. And also there is a parameter which is called sensitivity, which is directly proportional in this case to the voltage threshold, and the ratio between when I don't have anything hydrogen on the surface minus the thing that I have something with a different concentration. The other tricky part is that we work here in volume, right? We're in 3D in the moment, all of us, and we're XYZ coordinate. If you want to describe something on the surface, you need to transfer the concentration that's in 3D to the surface density or charge, because this is how the sensor works. And I'm not going to go in details in the paper, is discuss how they did it. And you have the concentration from 1 to 2 parts per million on the volume, and this becomes on the surface of the device something which is 610 to the 20 charges per cubic centimeter, and you have around twice to 1.221. So bottom line, you have directly proportional relationship between volume concentration and surface concentration, which is not new, but this is the way how it's transferred. Okay, voltage threshold, I don't know how this image is there, but probably I'm just going to show. So when you have trapped charges on the surface of the nanowire in this thing here, what is happening when you increase the number of the charges on the surface and you have a gate on the top, you screen the charge inside of the channel. Because you screen the charge with the dipoles that you have here, you need to apply more voltage in order to turn on the device. And what you see here is exactly the same. So if I take current compliance here, 10 to the -3 current, what I'm going to see is when I don't have any charges, the current is here, and the voltage threshold voltage less is here. When I increase the amount of the charges in the gate, I'm pushing to the higher voltages because I need to increase more the current because I'm screening the channel. And what you can see here, this is the voltage threshold is just moving slightly to the right. This is represented in bars here. It's exactly the same thing. So it's in the bars and it moves from something which is around, I don't know, 0.2 to something which is 0.4. So you have increase of the voltage threshold. So when you talk about transistors and memories, there are kind of 4 so-called figures of merit. One is I off, I on current, subthreshold slope, and this voltage threshold. So the other key figure of merit that you can look in this case here, which is called I on. So if you look here, I on, when you move from one device with no hydrogen to device with a lot of hydrogen, the I on decreases. I on to decrease is not good for transistors because it drains your battery, kind of, and I off very high is not good because it drains even more your battery. So, but this is a different story. So anyway, so here what you have is you have subthreshold slope increases. Sorry, the sensitivity ion current and sensitivity on the voltage threshold increases with the hydrogen concentration. So I promise I will finish on time. So I have just a couple of more slides. What you have here is the resistance, and the bottom line is that the resistance increases. So you can use the resistance in the device when you measure also to determine what is the concentration of hydrogen. You can use the transconductance. Again, you have a relationship between the transconductance, and you can measure this. And the other thing that you can measure or look at in more in details if you want to understand the physics is the band structure. So here, this is so-called band structure. This is a source and the channel and the drain. This is the conduction band, and sorry, the valence, and this is the conduction band. And when you modulate the gate, you change the potential barrier. I'm not going to go in details, but what is happening when you change the potential barrier. If you go further a bit, this is what things I wanted to show you. We have a different concentration here, and you have with and without band tunneling. So band-to-band tunneling is happening here between the channel and the drain. So this is what I said. In order to have the right behavior of the devices, you need to have the right physics. If you don't, band-to-band tunneling is quantum mechanical effect. If you don't have tunneling of particles through a barrier, which is quantum mechanical effects, you get wrong results. And this is what you can see here. If you have band-to-band tunneling or you don't have band-to-band tunneling, you have off-current difference of 6 orders of magnitude. So depends what you want to do. How you do it, this short channel effects kicks in different places. And again, my colleagues went further and they investigated what is the relationship of these IV curves when you make the device from 10, 8, and 6 nanometers. And what you can see here is that the off-current increases, which again is normal because if you think about it, what you have here is you have a channel which goes like this. You have a device which is omega gate. And what you do, you control the channel better when you have more gates on the side. And this increases the off current, which is better for your battery application. And here, what you have is the same story, but you can change the density or slash the concentration of the surface, as you can see, and you can see similar kind of behavior linked to the band-to-band tunneling and the concentration of the hydrogen. So, bottom line, what I want to say is that they did simulations. You can use simulations to evaluate eventually new concepts, eventually to match the results to this case hydrogen sensors. But what we do with Naveen, for example, we look in amino acids. So we're developing code. If you want to do DNA sequences or amino acid sequences, come and talk to us. We can do it in different shapes and forms and ways. And we work in European project which called Electromet, and Pedro knows some of the guys, that we also look in different sensors. So if you're interested in this, please come and talk to me. And thank you very much for your attention. 8